Okay, so in the previous few lectures we talked about supergravity, we talked about anomalies, and now our plan is to go back to the world sheet and to explore some of these things we learnt about in supergravity from the point of view of the world sheet. Okay.
Sir, I just want to make one comment about the supergravity and anomalies.
Yes.
So in 10D, from the analysis that we have done so far,
Yes.
it turns out that at least at the level of supergravity analysis, there are two more allowed gauge theories, namely U1 to the 248 cross E8 and U1 to the 496. But I think, in fact, it was more than a quarter of a century after the original anomaly consideration papers, it was shown that these theories are actually not consistent, and the only consistent supergravity in 10D are just the ones we get from string theory.
And what was there was a low energy proof that they were not consistent?
Yeah, it was a low energy and some consideration of gauge invariance. The proof came in 2010.
I see. I don't. It's not one of these swampland kind of things, right? It's not some conjecture. It's just a genuine inconsistency.
It's a genuine. So I mean, the point of the paper is that the 10D string swampland is empty.
Mm-hmm.
That even at the effective field theory level,
you can rule it out.
U1 to the 248 plus E8 and U1 to the 496 can be ruled out, and which is to say, which is a nice thing, because sometimes the detractors of string theory say that string theory is a theory of anything, but obviously that's not. The consistent theories are completely given by string theory. I think the authors had said that it's a principle of string universality.
Who are these papers by? Do you remember?
Washington Taylor, Oliver Daywolf, and some others I'm working on.
Yeah, interesting. So there's a more subtle anomaly.
Yeah,
somewhat subtle.
Yes, the anomaly cancellation. If people do it carefully, then they claim is that there's
some global anomaly or something like that.
Yeah, I think something related to gauge invariance and so on. I can.
Okay. Yeah, the kind of considerations that we talked about would have allowed those theories.
Yeah.
Yeah. Okay. I haven't looked at this papers, and that's interesting. That's interesting. So you say that just at the level of supergravity, you list all the anomaly-free theories.
Yes.
They all come from string theory.
Exactly.
In 10 dimensions. Yeah, that's interesting. I'll look at the paper. Okay. Excellent. Okay. Wonderful. What Upman is talking about is this. In our discussion of the anomaly-free nature of the SO32 theory, for instance, there was a rank minus some number. The number was, I think, 496.
89 minus 496.
Yes. Yeah. And the SO32 theory had satisfied that rank was equal to that 496. Yeah. So did E8 cross E8. Yeah. But there's another pretty trivial theory that does, which is U1 to the power 496.
Actually, that it's not just fair to look at in minus 496, because I think there are some other conditions that you had laid down and because otherwise we could have
looked at other
anything times whatever
SU2s and so on.
SU2 or something, and these would be ruled out by the other conditions.
Yeah, but the U1s are very are simple, because one of the other things we looked at was that this thing about the adjoint. Traces in the adjoint being represented into traces in the fundamental, and for the U1 all those things work out very simply, because all representations are, adjoint is trivial, everything is very simple, and it, as Upman said, at the level that we discussed it, it all works. If you just take many powers of U1, they don't spoil any anomaly cancellation condition.
They do make a note of this.
Yeah, it's as you say, it's a in the original discussions, they basically listed out the gauge groups that could satisfy the anomaly cancellation conditions, and many powers of U1 was one of the possibilities that never seemed to come from string theory. And Upman is saying that there is some more sophisticated consideration that shows that these U1 to the power whatever theories are from the low energy ruled out. I don't know of this consideration. That sounds interesting. There have, of course, been many discussions of anomalies recently. For instance, you know, if you take a single theory, well, this is not so recent, but this is the old Witten anomaly, but if you take a single fermion in 4 dimensions with SU2 gauge group. Okay?
Yeah.
This is not obviously anomalous from the point of view of traditional anomaly considerations. You see, if you take a single fermion, a fermion in the fundamental but no corresponding fermion in the anti-fundamental, charged in some way. If you take such a fermion, that theory is anomalous from the traditional point of view for the SUN theory for n greater than equal to 2. This is because fermions transform in complex representations for n greater than 2. Okay, fundamental representation and anti-fundamental representation are distinct representations. Okay. Exactly for SU2, they're not distinct. And yet, Witten showed that if you looked at more sophisticated anomaly considerations, that is, whether not the continuous part of the SU2 gauge group is realized correctly, but the global part of the SU. You know, SU2 differs from SO3 from the fact that there is one element in SU2 that is not in SO3, right? Which is basically rotations by 2 pi. Rotations by 2 pi is identity in SO3. It's a non-trivial element in SU2. And representations like the fundamental representation of SU2, the 2-dimensional representation, are precisely representations that make no sense strictly in SO3. Because when you rotate by 2 pi, you get -1. And if you are strict about SO3, rotation by 2 pi is +1, so it makes no sense for it to give you -1. But it makes sense in SU2, because rotation by 2 pi is a new group element.
Yeah.
Okay? So if you've got the fundamental, you have to have gauge transformations that involve this new element in some crucial way also being implemented correctly. Because the theory with the fundamentals is something you can consistently consider precisely because the gauge group is SU2 rather than SO3. And Witten showed long ago that there is a subtle anomaly associated with this global part of the gauge group.
This some sort of flipping that goes to the right and this Dirac kind of.
Dirac, yeah, it's some sort of gauge transformation that involves going all around and coming back to this identity element that you won't see from the kind of considerations we talked about, which were things connected to identity. Okay, so some theories have anomalies that you don't see from the considerations we discussed, usually associated with global factors, and maybe this is what Upanji is talking about. I'm not sure. Okay.
Yeah, I mean, they say that the cancellation of anomalies cannot be made compatible with supersymmetry and abelian gauge invariance. So using that consideration, such consideration.
Okay, so something else.
Yeah.
Okay,
I would love to have a lecture by you. I mean, if you.
I could look at it. Yes.
Yeah.
Okay. Okay. Excellent. But now let's continue. Okay. So we're going back to the world sheet. So let me just very, very quickly remind you of the basic elements of the world sheet. Okay. The world sheet had bosonic parts and fermionic parts. Right, the bosonic part were made up of the X mu fields, the B fields, and the C fields, and the B bar C bar fields. I'll never write the anti-holomorphic guys. Okay. The fermionic parts had the psi mu fields. Okay, and then we have the beta gamma system. Let us remember that the origin of the C fields was from infinitesimal diffeomorphisms. C was the fermionic counterpart, anti-commuting counterpart of a vector field. Okay, it's an index up. So C had a dimension of C was equal to -1. On the other hand, B was an infinitesimal change in the metric, 2 indices down. So the dimension of B was 2. Okay. Now, gammas were the fermionic counterparts of C. Okay. It's like some sort of fermionic vector field. So gamma dimension was minus half. Okay, and beta was like some change, not in the metric but in the superpartner of the metric, which is a spin 3/2 field. So the dimension of beta was equal to 3/2. Okay. Now when we studied the beta gamma system, one of the things that we did was bosonize it. Okay. By which let me remind you. So the bosonization of the beta gamma system, where was that? Here. Okay. So what we did was we wrote beta as equal to e to the power minus phi times del zeta, and gamma was equal to e to the power phi times eta. Okay, and the zeta and eta themselves made made a BC system. Okay, so zeta and gamma and eta, sort of like a BC system, except that one of the weights were different from those of B and C. The weights in this case, one of them was 0 and the other one was what was it, 1 minus 1. Let's remember. Yeah, 1 and 0. So eta, dimension of eta was 1 and zeta was 0. Okay. Then you remember that there was one more subtlety in this whole Okay. First let me remind you, and then you remember that there was one more subtlety in this whole game, which went as follows. In vertex operators for matter fields, okay, in vertex operators for matter fields, what basically appeared was the e to the power minus phi. Okay, but because zeta was sticking to the sphere for a moment, you remember that on the sphere there were 3 zero modes of C and no zero modes of B. Okay, and the 3 zero modes of C were related to the fact that C had dimension 1. Okay, what were these 3 zero modes? They were the zero modes were C is equal to C naught plus Cz plus Cz square. All these zero modes were potentially irregular at infinity, but because of the transformation property of C, the tensor transformation property of C, this apparent blow up at infinity was actually tamed for these 3 modes. Okay, the taming happened because it had dimension 1. Okay, if you have higher and higher dimension, you get more and more taming, right? Because there was some inverse factor that was proportional to the dimension. If you had higher and higher dimension, you would get more and more inverse factors, and so you'd be able to go to higher order and have more regular fields. On the other hand, if you had lower dimension, you get fewer factors, and in particular, if your dimension was 0, you get no inverse factors. Okay. What? Yeah. By sorry, higher dimension, I mean higher negative dimension. If you went to -2 or -3 or -4, you would get higher and higher powers of these guys. In fact, if you went to -2, you would be able to go up to z to the 4. If you went to -3, you'd be able to go up to z to the 6. Okay. On the other hand, positive dimensions didn't allow anything. That's why B had nothing, right? Okay. Now let's look at this eta gamma system here. This eta here is positive dimension. No zero modes on the sphere. But this zeta here has dimension 0. So this is very simple. Exactly eta 0 would be allowed. Okay? So you remember that there was one complication was which was that this zeta here had a 0 mode on the sphere. Okay? And there is a counterpart of all of this in higher genus Riemann surfaces, but we won't get into that for now. Okay. This zeta had a 0 mode on the sphere, and for that reason you might think, well, all our correlation functions are going to be 0, because none of the vertex operators have a factor of zeta inserted in it. And there is a 0 mode, so that'll give you 0 path integral. But you remember that the resolution to that was that if you had some number of insertions that along with the insertions associated with the actual vertex operators of string theory, we were instructed to put a single zeta insertion just anywhere on the world sheet. Now this looks like a strange thing to do, because it looks like the answer is going to now not be a 3-point function but a 4-point function. But precisely because zeta, okay, appears nowhere else, and to get a non-zero answer we have to saturate the 0 mode part of the path integral, the zeta here can be replaced by its 0 mode. And its 0 mode was constant on the sphere. Okay, so the answer didn't depend on where we inserted zeta. So we were instructed to insert the zeta. It didn't matter where we inserted it. Then there was this other sort of nice fact. You remember we had these picture changing operators. The picture changing operators went like this. You took a zeta insertion, and then you took j BRST and you integrated around zeta. Okay? And then we had these contour manipulation ideas, which went this way. You can take this contour that goes around the zeta and then try to close it round the other way around the sphere. All the vertex operator insertions are okay because they're all BRST closed. So the little potential problems when you circle these vertex operators will all give you 0 because they're BRST closed. But this guy will not. But all that you've done, so you know this is equal to but all that this operation has done is to effectively move your BRST or your picture changing operator location to where your original zeta insertion was. But the path integral didn't care on where didn't care about where your original zeta insertion was. And so this manipulation has shown you that the answer to that if you have a picture changing operator inserted somewhere in your path integral, the answer to the path integral doesn't care about where you put the picture changing operator. Okay? The same thing works for multiple picture changing operators, because any given picture changing operator is BRST closed. So you can treat it like one of the vertex operator insertions. Okay? And you remember that our final rule for string perturbation theory was that we needed to saturate the beta gamma, the phi, in order to get the phi, a non-zero answer, we needed to have the right number of powers of phi. Okay, and so we could put our vertex operators in any picture that we wanted. Okay, but then put sufficient number of picture changing operators. Put sufficient number of picture changing operators so as to ensure that the total phi power came out to be correct. Came up to be, I think, on the sphere phi squared 2, the total power of phi's. Okay, so you had to put the right number of picture changing operators to ensure that. Okay, And then we also talked about how you could take vertex, if you wanted to think in that language, you could take the vertex, these picture changing operators, and take them near to one of the vertex operators. And when you did that, you got the vertex operator in the new picture. These picture changing operators effectively changed the vertex operator, give you equivalent results, but increasing the Gauss number of the not the fermionic Gauss number, the phi number of this vertex operator. So for instance, in the NS sector, our bare picture changing, our bare vertex operators always came with an e to the power minus phi, and then the matter superconformal primary. In the Raman sector, we had e to the power minus phi by 2 times a superconformal primary. And then you put as many picture changing operators as you needed to saturate the total phi Gauss number. A picture changing operator increases the e to the power minus phi power by 1. So this was the vertex operator of the minus 1 picture. We also talked about vertex operators in the in the 0 picture. In the NS sector, and we could talk about vertex operators in the half picture if you want, or the 3/2 picture in the Raman sector. Okay, now before turning to the real material that I want to talk about today, I want to tell you about something, an irritating thing about the formalism that we're studying. And that goes as follows. Although we haven't yet studied in detail, we will as the lectures progress, string theory can be formulated not just in flat space, not just for strings propagating in flat space, but on any solutions to Einstein's equations. More precisely, if you remember our no-Gauss theorem, we proved our no-Gauss theorem for the sigma model on R 1,1 times any CFT with C equals 24. So at least in such spaces, you can just replace the CFT of strings propagating in 24 free dimensions with any C equals 24 conformal field theory, and that will give you a good string background. Okay, and there's a similar statement for the superstring. You take R 1,1 as a supersymmetric sigma model and replace the R8 part with any C hat equals 8, n equals 1 superconformal field theory. Right? Now this is nice and abstract, but you might wonder, is there a way of not talking about generally the space of all consistent string theories, but theories near flat space? So for instance, if we want to work in some solution around flat space, maybe a black hole, we want to do string theory in the background of a black hole, or there's a strong gravity wave, we want to do string theory in the background of strong gravity wave. Okay, how do we do that kind of string theory? Okay, so there is this very beautiful connection, and which has limitations. The limitation I wanted to tell you about. But first, let me tell you. I'm sure all of you have heard of it, but at least maybe we even had was it this class or the previous one? Did we have a presentation on this? Pranjal was not a part of this class, right? No. I think Pranjal gave a presentation in the previous one. Yes. Right. So there is this very beautiful connection which goes as follows. Suppose instead of taking, I'm saying it in the context of the bosonic string, but everything generalizes. Okay. Suppose instead of taking, suppose we consider the generalized world sheet theory, which is del alpha x mu, del beta x nu. And why stop at this? Let's turn on, what's a b mu nu of x, eps, and this has g alpha beta.
Yeah.
This has
World sheet matrix.
exactly, del beta x nu, and here there's an epsilon alpha beta. Suppose you try to define string theory, and there's the same 1 by 4 pi epsilon alpha prime and so on. The discussion, schematic. Suppose you try to define string theory starting with the world sheet theory, which is here. The special case G being constant and B being 0 is what we've discussed. In parts of the discussion, we have generalized to G being constant and B being constant when we looked at Narayan compactifications and tori. But you can, I mean, why stop there? Let's take the most general theory like this. What could possibly go wrong?
And yeah, no, and you are not allowing for any other coupling to R.
The dilettante. Yes, if you were to study, right, so we could also turn plus phi R, right? Yeah. Though most of the time I will discuss only string theory on a flat background metric, so you will not easily see this.
Right.
Okay, but you'd see it in the stress test. So yes, so that as well. Okay, so now you can ask, well, let me study this. What can go wrong? Now, you see, first you should understand that something should go wrong. Because it should not be possible to study string theory in an arbitrary space-time background, an arbitrary B field. It should only be possible to study it in solutions to the string equations of motion. Right? Why is that? That's because there's no such thing as off-shell gravity. You can take field theories and take them to any configuration you like by turning on sources at finite positions. By turning on sources everywhere, you can generate basically any configuration you like in a field theory. But because gravity can only consistently couple to conserved quantities, and if you turn on a source, whether the thing you couple the next thing to will be conserved, will depend on what's going on. Basically, in gravity, you are only allowed to couple things far away, at infinity. Only S matrices, at least of the simple observables of gravity, are well-defined observables. You can't turn on sources in gravity. This is true both classically and quantum mechanically. It's a true quantum statement, but it's also a true classical statement. To turn on finite correlation functions in gravity, even classically, are just not well defined. Okay, because you violate conservation of the stress tensor. Okay, so
I mean, I was just wondering, would another equivalent of the statement be that, we must be doing string expansion around the background generated by string theory itself?
But I wanted to emphasize that would not be true in a quantum field theory. Because in a quantum field theory, you could turn on sources to work in more or less any configuration you wanted.
Right.
Here, you're not allowed to. You're allowed maybe to send things from infinity. But then what happens in the middle happens. That's exactly what you said. Okay? You've sent something in, but then what happens in the middle should be evolving around by equations of motion. You're not allowed to change those equations of motion by suddenly turning on a source in the middle. Okay, so you can't do what you want. Okay? Because of that, okay, it shouldn't be allowed to study string theory in any background because it's the theory of gravity. You should be forced to work in a background which obeys the string equations of motion, or as Upanyu said, is generated by the modes of the string theory itself. Something has been sent in and does what it does. So it shouldn't work. But what technically could go wrong? And of course the answer is that, well, we guarantee that string theory works, provided what we get is a conformal field theory with the right central charge. Now you take a two-dimensional theory like this, okay? You take a two-dimensional theory like this, and in general it is not a conformal field theory. Also in general it doesn't have the right central charge. But the more serious question is it a conformal field theory? Okay? Now, let's think of this two-dimensional theory as a two-dimensional theory. As you know, in a field theory, in general dimensions, the theory, the couplings that you are allowed to turn on, if you want to think of the field theory as generated as a flow from a fixed point, are the relevant and perhaps marginal couplings. Okay? So the first question you might ask is, what is this? How many couplings have you turned on? Well, we've turned on an infinite number of couplings. Because every Taylor expansion coefficient of G mu nu of x, from the point of the two-dimensional theory, is a new coupling. Now, normally, I mean, in a civilized dimension, 3 and higher, there's only a finite number of relevant couplings you can turn.
In 2D, there are infinitely.
But in 2 dimensions, the dimension of the operator x is 0. Actually, operator x is not well defined, as you know, it has these log singularities. But to the extent that you associate a dimension with it, it's 0. Right? So, it's not clear that there is any bound to the number of coefficients you can turn. Because x to the power n also has at least naively dimension 0. Okay? So, this is a theory with an infinite number of relevant couplings. And there's some very non-trivial renormalization group flow equations that would appear in such a theory viewed as a quantum field theory in 2 dimensions. Now, how do we a conformal field theory is a theory where this flow is it doesn't flow. You reach a fixed point. Okay? Exactly. So now the first thing that you want to understand is, can we do any calculations in such a theory? We've got this infinite number of couplings. Can we calculate? Can we calculate the beta functions? Well,
string perturbation theory, in alpha prime, or where in alpha prime.
Exactly. So here we've got this 1 by 4 pi alpha prime here. Now, you see, if this object here, if this x, if this G mu nu is constant on length scales large compared to alpha prime. Okay, if first you see that alpha prime goes to 0, is at least formally a weak coupling limit. Because in any Lagrangian, you take 1 over g squared as sitting outside and g going to 0 is the weak coupling limit. But of course, alpha prime has dimension full. So alpha prime goes to 0 is not very contentful. It has to be compared with something. What is it compared with? Well, this whole thing becomes non-trivial only when G mu nu varies in x. So there is a length scale of variation in the problem. So if alpha prime is small compared to that length scale of variation, this Lagrangian is effectively weakly coupled, because patch by patch at least you can treat this Lagrangian as being sigma model in flat space, patch in target space. And then there are only small variations, small ripples around that. Okay? Not completely clear how to turn these words into calculation, but you can at least roughly imagine that this is the case. And it turns out to be true that there is a calculation you can reasonably do. Okay? You can do. It's a beautiful calculation actually, done in the 1980s.
Made up of this G mu?
No, this R is the world sheet metric. You can for a moment forget about this. Work in flat space. First flat world sheet and forget about it. Okay? So you can imagine that there is some reasonable, there is a beautiful calculation actually you can do. It was done by various people, but okay, various people. I think Ashok played a role. He doesn't get much credit for it, but I think he played a role in this calculation. But Callan and Thorlacius, various other people. Okay, but you can do this calculation, and when you do the calculation, you find that you get equations like this. G mu nu dot, where dot now means evolution under RG flow, is equal to alpha prime R mu nu plus blah blah blah.
Yeah, I mean, this beta mu nu of the variation of the G, of the G mu nu field of the induced metric of the world sheet.
What?
No, I mean, this is basically the beta function of mu.
It's the beta function of all the couplings that appear in G mu nu.
Yeah.
G mu nu has an infinite number of couplings.
Yeah.
But you know, the structure of the calculation is such that you're guaranteed to get something local.
Yes.
Local not in target space,
In X.
but in space-time. It's an amazing thing actually. You know, so if you thought of these couplings as the Taylor expansion coefficients, you
And
can.
it will be n by n. Like, I mean, if you put g mu nu n, you are saying you will get r mu nu.
N meaning nth derivative? What do you mean?
I am saying if you Taylor expand it.
Yeah, this is the functional equation.
Okay.
It's a local functional equation. Now you Taylor expand both sides if you want.
Yeah.
Okay? You get something local in space-time. This is what allows it to be a manageable equation, right? If you just thought of it as a bunch of coefficients and a matrix, it's some horrible stuff. But you get locality in space-time free. And this comes from the same thing that I told you about. The patch by patch is hardly flowing. And in a little patch, things are varying, controlled by the derivative in that patch. And that ensures the locality. Okay, but there's some beautiful calculation here. There's also an H, mu, alpha, beta, H, nu, alpha, beta kind of thing here. And so on. And then there's a B mu nu, there's an evolution of B mu nu, and so on.
No, but that appears at order alpha prime square, right? This H
Uh,
square.
No, H is one derivative. R mu nu is two derivative. Each H is one derivative.
I see. So no alpha.
No, it's the same alpha prime.
Same alpha. Sorry.
Same alpha prime as R mu nu.
Huh.
Okay, it's just derivative counting.
Yeah.
mu is the derivative of b mu nu.
Yes. Okay, so all these things mix. But you know, the really interesting things is that these things become zero at leading order and alpha prime. The condition for that is that Einstein's equations are obeyed. Einstein's equations
Yeah.
and the B mu nu equations of motion are obeyed.
Why
So-
there is no t mu nu kind of?
Why what?
Like Einstein equation is not only r mu.
Why is there no T mu nu? Because you know, in string theory, T mu nu comes from the fields of string theory. So this is T mu nu,
Okay.
but T mu nu from the B field.
Yeah.
Yeah, you see, it's not. We're not doing like what the classical GR people do. You throw any
Yeah.
T in. What we have is what we have. There's nothing else. Okay, and similarly, yeah, it's amazing. Similarly, when you calculate the B mu nu equations of motion, B mu nu dot, you get something, but it closes on the B mu nu equations of motion. Now, why did I tell you all this? I told you all this because now the question of formulating string theory in a background that is not flat space but some reasonable solution of Einstein's equations is now clear how to do. What you do is to work with this action where you put a solution of Einstein's equations. Now, by the way, if you work to higher and higher orders, you will get corrections to Einstein's equations. And because you get an alpha prime square and alpha prime cube. And the corrections to all orders corrections to the equations of motion can be thought of as simply coming from the requirement that this two-dimensional world sheet theory
Is a CFT.
is a conformal field theory. So all orders corrections to Einstein's equations are encoded in this very simple formal statement that this two-dimensional field theory is a CFT of central charge 26. Isn't this a beautiful statement? It's a remarkable thing, in my opinion. A remarkable thing unifying two-dimensional physics and 10-dimensional physics. I mean, you can forget about everything else. Just the fact that there's this remarkable connection between Einstein's equations and its connections and its corrections and RG flows on two-dimensional sigma models. It's quite an amazing thing. It should make you sit up, right? Okay. So in the bosonic string, we are able to perform string theory not just on curves on flat space, but on background fields, on backgrounds of Einstein's equations. Backgrounds which are solutions of Einstein's equations.
So, could you please comment on some of the other exact backgrounds admitted by the string? I mean, this week obviously we heard about ADS3 times S3 times some T4. So, what are some of the other?
So, for instance, a Calabi-Yau solution. A Calabi-Yau solution, it has been argued that associated with any Calabi-Yau, there is a corresponding. You can correct that order by order to to retain a supersymmetric solution of Einstein's equations. So if you are interested in studying string theory on R4 times the Calabi-Yau, this is what you should do with the Calabi-Yau method. Or K3. Okay? Yeah.
Yeah, K3 would be four dimensional. I mean, if we want to do some 6 on 6D.
If you are interested in R6 times K3.
Yeah, but I mean, just this on the worldsheet level, obviously there must be hundreds of exact solutions known by now.
Yeah, worldsheet level, hundreds of exact solutions.
I mean, I don't know.
Yeah, no, not so many.
I see. Okay.
Yeah.
They're very rigid in some sense.
You know, in the end, 2D conformal field theory is like, no, it's not rigid, it's just a lack of understanding.
I see.
You know, people sometimes think that we know lots about 2D CFT. It's not true.
Oh.
We know lots about 2D CFT with C less than 1. All theories are understood. But you go for C, look at C greater than 1, you know very little. So for instance, the Calabi-Yau solutions we know because of supersymmetry. Such analogous solutions that are not supersymmetric, things that are time dependent, we know very little. Very little is known.
So this ADS3 is obviously one of the known exact backgrounds.
Yeah. So when you have current algebra, that gives you new technical power. Yeah. So Wessel-Witten theories we know. Okay. Minimal models we know, and then maybe some here and there things involving like these Calabi-Yau solutions. Okay. But not too much.
I see.
Okay,
so
that's exactly.
Just wondering, is the PP wave solution a part of this 2D CFT background?
Yeah, now these PP wave solutions are associated typically with Ramond fluxes, at least the ones that were studied in great detail. That's what I want to get towards telling you about. Sure. So, fine. Okay, excellent. So far we talked about the bosonic string, but we're interested now in the superstring. Okay, so suppose you turn on a background of the NS fields. You can always take these. Okay, first, one last thing. You see this G mu nu, as we've seen, is some solution to Einstein's equations. So if it was a linearized solution to Einstein's equations, what you would get is G mu nu plus H mu nu.
Yeah.
And H mu nu, being a solution to Einstein's equations, is the same thing as being a 1,1 vertex operator in the conformal field. Because there's a one-to-one correspondence between 1,1 vertex operators and linearized solutions to the space-time equations. So from that point of view, the way we're generating these new CFTs is clear. What we're doing is taking the CFT and adding to it marginal operators, and then working hard to ensure that they remain exactly marginal.
I mean, why this Armenian is so special that they don't involve any other higher order terms?
Why higher order terms? You see, it's because of derivative counting. We have only calculated this to first order and alpha prime. So you have, on the right hand side, you have to be something that's diffeomorphically invariant. And two derivative. What are the options? Okay, right? Okay, but at next order you'll get more things. It's just the same way we count higher derivative corrections to Einstein's equations. It's that same kind of thing. Okay. One thing that is less clear, from this point of view, it's less clear that the equations of motion come from an action. Okay?
Right. Yeah, I mean, to actually covariantize this action to the space.
Well, you know, in classical physics, you get a great deal of information just from knowing that your equations of motion come from an action.
Yes.
Here, it's not so clear. Because, for instance, what does it mean? It means that, suppose you've got an alpha phi coupling, where alpha and phi are two fields. This tells you that when you vary with respect to alpha, you get a phi. So you get a phi in the alpha equations of motion. You cannot not also have a phi in the alpha equations of motion. Maybe I said that. An alpha and the phi equations of motion. Because it comes from a term in the action. A set of equations of motion where the phi appears on the right hand side of the alpha equations of motion, but no alpha appears on the right hand side of the phi equations of motion, unless you do something very clever, will in general not come from any action. So things coming, the fact that equations of motion come from an action is not just a convenience. Maybe it's not emphasized enough in like Goldstein, for instance. But it is in Landau editions. It's not just, that we are writing these equations of motion in a more elegant way. It's a new principle of physics. That all the equations of motion of the world come from an action. In the end, that is justified by quantum mechanics. Okay. So even on the classical level, that equations of motion come from an action is not, like I said, it's not a convenience. It's a completely, it carries content. That statement carries content. Here, when we get these beta functions, I get one set of beta functions for G mu nu.
Yeah, and there will be
one for B mu nu. How do we know that the beta functions are connected?
Does any equation of motion can be written in terms of
No.
No. There's only one.
Let me give you an example. X double dot plus X dot is equal to 0. If this is the only field in the problem, there's no action that will give this to you. Let's try. X dot square will give you the X double dot. And you might think, what about X dot? That should give you the X dot. But it doesn't. One way to see it doesn't is because you can see that this is a total derivative. d by dt of x square by 2. And if you do the calculation, when you vary with respect to this, you get an X dot. But when you vary with respect to this, you get a minus X dot. So you get 0. Okay? So this is a nice equation of motion described as a damped harmonic or whatever. No action will give it to you. Unless you increase the number of degrees of freedom.
Explicitly include some time dependence in that.
Or you increase the number of degrees of freedom.
No, yeah.
If you add X double dot plus X dot times Y,
Yes.
then the Y equation of motion does give you this. The problem is that now the X equation of motion will give you an anti-damped equation for Y. And so you can get, with the condition that there are no other fields, no action in the world. So many equations of motion just don't come from any action. There are many more examples you can come up with when you involve two fields. Like we said, something with one field in the source as a source for the other guy, but nothing on this side. No action will give it to you. Okay? So here we're getting these things. However, people have, by studying the structure of renormalization group flows, come up with formal proofs that the equations actually do come from an action. And indeed, at lowest order, you can write down the action that generates it. It's gradient flow, in fact, from the action, and the action is Einstein's action. So when you get these beta functions are gradient flow on a functional that involves Einstein's action. It's actually a very beautiful story.
Yeah. Einstein action plus, including the H mu nu, this three-form square.
The whole Einstein
Yeah.
action.
Yeah.
The Einstein action with the matter. It's gradient flow with some metric on the space of fields. Yes.
I think so. The space-time theory
Yes.
is the classical, like the 10-dimensional theory
Yes.
of G mu.
Yes.
Where does G mu nu, capital G mu nu come from?
Yes.
That is coming from some equation of motion, and it's a classical solution of, let's say, Einstein's
Good.
equation. Don't we have, like, how is the quantum mechanics of worldsheet capable? I would assume that just doing string theory we should be able to manipulate capital G mu nu in some way, right?
What do you mean manipulate?
Change it by some, perturb the.
Any way you want, you're saying.
Yeah.
Well, this is one attempt to do that. And it doesn't work. Because it'll give you answers that are nonsense unless this worldsheet string theory is conformal. Now, why, when you say I would have imagined this, if you thought of string theory as a theory of gravity, you shouldn't have imagined this. Even classical gravity has trouble with sources.
Yeah.
That's why we study electromagnetism. We can ask, what happens in electromagnetism? What is the electromagnetic response to a charged particle moving on this trajectory? This is a well-posed question. Jackson studies it. Ashok told us about it. If you ask, what is the gravitational response to a test particle moving like this? The answer is, beyond linearized order, it's an ill-posed question. Because you will not get, once you take the back reaction into account, you will not get a conserved stress tensor. gravity, turn on sources any way you want. The things that you source gravity have to then obey their own equation of motion.
Yeah.
Even in classical gravity, again something not very much emphasized in the study of general relativity. It's a simple fact about classical gravity. And remains a simple fact about, I mean maybe not simple, but a fact about classical string theory.
Okay, yes.
Okay? This is not a quantum thing. It's a simple classical statement.
Yeah, I get it.
Okay, let's keep going. So I just have to get to the point. I'm sorry I've taken such a long time on this diversion. We have to get back to the real stuff, but let me just tell you since we've come so far. Now, if you turned on a background field like this, in the NS-NS sector, the rule is move to, okay, so I was telling you that this G mu nu, if we took it to be eta mu nu plus H mu nu, what you're doing is turning on a linearized solution of Einstein's equation, which was just a vertex operator. In the bosonic string, that's great. It's a vertex operator. But in the fermionic string, you can immediately ask, vertex operator in which picture? Now, in the NS-NS sector, there is a natural picture. It's the zero picture. To see why it's natural, we'll contrast it with the RR sector in just a minute. The rule we give is to turn on the vertex operator in the zero picture. And indeed, I don't know if you remember those classes, but when we looked at the zero picture, when we looked at the minus one picture, let's say for the graviton, the vertex operator was psi mu, psi bar, nu, e to the power minus phi. Looks very different from turning on del x, del x. Well, psi, not del x. But if you remember, going from the zero, from minus one picture to the zero picture involved acting with g minus half. And g minus half had terms which annihilated a psi and created a del x. But you had to act with g minus half and g minus half tilde. So it annihilated this sign, created a del x, annihilated this sign, created it. And so in the minus half picture, there were terms involving fermions, but there was also a term which was. So in the zero picture, the vertex operator corresponding to a graviton looked very much like that of the bosonic string, and indeed looked like changing the metric of the sigma model. And in fact, what you got was a supersymmetric completion of this. It was this integral d2 theta. So the fermions followed from supersymmetry, from worldsheet supersymmetry. So it's exactly what you wanted. Okay? So if you want to study motion of strings in background NS-NS fields, no problem. It's as easy as for the bosonic string. However, for the Ramond fields, there is this very irritating thing. And that very irritating thing is that there is no such thing as a zero picture. Because the bare Ramond operator comes with e to the power minus phi by 2. Then any number of picture changing operators you do, you can't make that zero, right? Because picture changing operators change phi power by an integer. Why is this a problem? This is a problem for the following reason. If you exponentiate a vertex operator with non-zero phi charge, then now imagine expanding it in a Taylor expansion. Suppose you start with charge half. The term which is linear in that thing carries charge half. The term that is quadratic carries charge 1. The term that is cubic carries charge 3 by 2 and so on. But as you know, when you do a scattering calculation, the total phi charge has to add up to minus 2. So only one of these powers can possibly contribute to the calculation, which makes no sense, which means you haven't really exponentiated. Exponentiation is precisely the idea of carrying all powers. Right? In the NS-NS sector, by going to the zero picture, okay, this works. what you would somehow need to do is also exponentiate picture changing operators or some crazy stuff. For any given amplitude, you always know what to do. But it's this exponentiation, because there's no such thing as a zero picture for the Ramond fields, that gets extremely complicated. And people haven't figured out how to correctly do this. For this reason, this NSR formalism, while it's great for computing things in flat space, or in theories with only NS background fields, is basically useless for computing in backgrounds involving Ramond fields. Okay, and this is one of the outstanding questions that people keep asking every once in a while. How do you effectively deal with string theory in background Ramond fields? Okay, now we had these talks recently by Rajesh, in which even though he was studying string theory with background NS fields, he found it useful to go to some other formalism, this hybrid formalism, for some reasons of his own. However, if you were interested in studying string theory in ADS5 cross S5, which is supported by Ramond field, you wouldn't have the option. This NSR formalism doesn't exist for that situation. You would have to use some other formalism. Such a formalism maybe exists, this Berkowitz formalism.
It's pure spinner.
Pure spinner. It's very complicated. And it's not clear that it's completely well defined. There's this so-called big host problem in the Berkowitz formalism. You know, so the problem of getting an effective, useful description of propagation of strings, classical propagation of strings in background Ramond fields, while there are some formal solutions to this pure spinner stuff, is in many ways really an open question, at least for practical purposes. And this is something we should keep in mind. Okay? This whole formalism that I've built up for you over these lectures, very effective in some situations, effectively useless in others. And would be great to have an effective formalism that is as elegant and beautiful as this one for background Ramond fields. We don't yet have one. Okay, so this long diversion occurred to me because of the minus half. I thought I would tell you about it. Okay, but let's any questions, comments, or we get back to on track. I'm really sorry. I've spent an hour on this. Okay.
You're also.
Yeah.
Questions are always.
Okay, but fine, fine. So let's get back to where we wanted to be. So I've tried to give you a very quick reminder of the structure of string perturbation theory. I mean, of vertex operators and so on. Anything else we need, we'll remind ourselves as we go along. Okay, fine. Now what I wanted to do was to remind you of the is to start discussing a little bit more about the vertex operators of massless physical states in the superstring. Okay, so these vertex operators in the NS sector we understand quite well. And it's basically the psi mu, psi bar nu in, let's say, the -1 picture. And then the symmetric part is the graviton, the trace part is the dilaton, the antisymmetric part is the B mu field. We've seen this on many occasions. But we have not really focused our attention on the massless vertex operators involving Ramond fields, and in particular in the Ramond sector. Okay, and this is what I wanted to start by telling you about it. Okay, so let us remember in the Ramond sector, let's say in the -12 picture, the vertex operators I to the power -5/2 times, you will remember it was e to the power I and sum over SA HA. A is equal to 1 to 5, and all these SAs You remember how it worked, right? This had scaling dimension 3 by 8. This has a scaling dimension 5 by 8 because e to the power SAH has scaling dimension SA square by 2. SA squared is 1 by 4 and then by 2 it's 1 by 8 and there are 5 of them. 5 by 8 and then made up 1, 1. Then you remember how that worked. Okay? Now, let us, okay, this is good, but you remember that physical states also obeyed the minus 1 to the power f. Okay? The minus 1 to the power f is equal to 1, or in the Ramon state 1, or effectively minus 1. So basically a definition, chiral or anti-chiral. So let's see how this works here. Okay? Our minus 1 to the power f, you remember how we defined it in a clean way. It was the net power of momentum for all the fermionic fields. Okay? So this f was equal to, in this case, minus half plus sum over A SA. Okay? Now, our GSO projection demanded that this whole thing be either, minus 1 to be either an odd integer or an even integer. It's already good because it's clearly an integer, because there are 5 essays. So it's clearly an integer. And now when will we get an odd integer and when will we get an even integer? Well, let's take, so there's minus half, and let's take all these essays plus. Okay? So we get plus 2.5, which is 2. Okay? So all essays plus gave us plus 2, gave us an even integer. Now if you flip one essay, that flips s by 1, because half goes to minus half. So it changes f by 1.
Yeah.
Okay? But if you flip 2 essays, that flips s by 2. So it's clear that all states that are half, 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 yes, half, half, or are related to this by an even number of flips, carry the value, by my definition, minus 1 to the power f is equal to plus 1. Okay? So, the physical states, so let's say we're working with the NSR sector for a moment. Okay, so the NS sector we understand. Okay, we've on the left side we've imposed our minus 1 to the f. The NS sector we know very well. We're not focusing on that. Now we're focusing just on the right side, where we have the Ramon sector. Okay, the physical state is all states like this. Okay, with the total number of pluses being odd, or the total number of minuses being even. Okay? Now, let's take a minute to interpret that condition. What does it mean that the total number of pluses is odd, or the total number of minuses is even? Okay? So let's see. Let us remember where these h's came from. These h's came from taking dimensions in pairs. There was psi 1 and psi 2. We bosonized this and we got h1. Okay, there was psi 3 and psi 4. We bosonized this and we got h2, and so on. Okay, and let us also remember that effectively psi 1, psi 2, this current mapped to del h1. And same for the others. Now, what is this current here? Can you see that this current effectively rotates in the 1-2 direction? right? Because psi 1, psi 2 is same as psi 1 to psi 2 minus psi 1, psi 2, psi 1 because of anti-commutativity. Okay, and its action on any of the psi's will be to replace a psi 1 by a psi 2, but a psi 2 with a minus psi 1, which is exactly what a rotation in the 1-2 plane would do. Okay, so what is this del H1? The charge under del H1 is simply angular momentum carried in the fermion sector in the 1-2 plane. Okay, similarly the charge under del H2 is angular momentum in the 3-4 plane and so on. Now these essays were the quantum numbers under the currents del H1. Right? The essays are the charge under the 0 mode of the current del H1. It's momentum. So these essays have a space-time interpretation. They are angular momentum in the 1-2 plane, angular momentum in the 3-4 plane, angular momentum in the 5-6 plane, so on. Otherwise known as spin right. So these essays are spin quantum numbers in a particular choice of Cartan, where the Cartan is 1-2 plane, 3-4 plane. Okay? And these, our massless states, came in a multiplet with our essays being plus minus half. Okay? So now the first question you can ask yourself is, what multiplet of the 10-dimensional rotational group do you know of in which all charges are either plus minus half? So what is the name of that multiplet? Spinor. It's a spinor multiplet. So this combination of essays, with essays being plus minus half, is in the Dirac spinor multiplet representation of SO10. Is this clear? Now what's the deal with this minus 1 to the power f is equal to 1? No, not all states. Or okay, only those with minus 1 to the power f is equal to 1. Okay. So minus 1 to the power f is equal to 1 actually restricts us to a particular multiplet. Remember that in even dimensions, Dirac spinors are not in a particular representation of the gauge group. It's sum of two representations, chiral and antichiral. Okay? And the condition that minus 1 to the power f is equal to 1 is the chirality condition. How do we know that? Remember that the operators, where did we get, by the way, this spinor representation from? One way of thinking of it is that came from the 0 modes of the fermionic operators. In fact, that's how we got it right. Okay, so we got it from psi 0 mu. Okay, and these psi 0 mu in the spinor representation are implemented by the operators gamma mu. Now minus 1 to the power f is an operator under which every psi 0 mu carries charge minus 1. In other words, an operator that anti-commutes with every psi 0 mu. So by definition, minus 1 to the power f is the operator such that on this sector, restricted to the 0 mode sector, otherwise more generally without the 0, but restricting to the 0 mode sector, this is true. Because it's just the statement that if you take minus 1 to the power f and act on psi 0, you take it through, you get an additional minus 1. That's that statement that this is equal to 0. But do you know of an operator on the gamma matrix sector that implements this? Gamma 5, or in this case gamma 11. Right? So this minus 1 to the power f on the Clifford algebra sector is implemented by gamma 5, or we'll call it gamma 11. But what is the condition that minus 1 to the power f on psi is equal to 1? It's the condition that gamma 11 on your spinner is equal to, sorry, it's not 1, it's psi. On your spinner is equal to the spinner. What is the name?
The chiral.
Exactly. What is the name for such spinners? They call chiral spinners. So you see very explicitly that the condition that minus 1 to the power f acting on physical states is 1 is a chirality condition on spinners. Okay, so this, this is what makes string theory beautiful. There's this constant interplay between natural worldsheet concepts and beautiful space-time concepts. This minus 1 to the power f, you remember all the considerations that went into imposing this GSO projection. From the point of view of space-time, it's such a natural thing. You're not working with the most general Dirac spinner, you're working with chiral spinners. So that interplay is what makes you sure that you're doing something good. Okay, great. Fine. So in the Ramon sector, massless modes come as chiral spinners. Now, chiral spinners are good, but we're not just doing representation theory, we're doing dynamics, right? So they should obey an equation of motion. Where does that come from? Okay, sorry. Well, of course, it comes from the condition that the spinner be BRST, that be annihilated by the BRST operator. But as you remember, if you choose canonical choices of vertex operators, let me remind you, for the bosonic string, the condition that an operator be BRST closed was in the end the right condition. But we could always, in BRST equivalence class space, choose canonical operators of the form C times V. Okay, you could always choose such representatives. Okay, and then the condition that it be BRST closed amounted to the condition that this just be a 1,1 primary operator. Okay, that it be annihilated by all ln's for n greater than 0, and that L0 acting on it gives a definite value. Okay, so there is a very similar consideration for the superstring. Okay, by choosing your canonical choice, that is this e to the power minus phi in this case, and c. So c times e to the power minus phi times v. Okay, you get the condition that this guy here be a vertex operator that is primary under the full superconformal algebra. Okay, so under the full superconformal algebra, the ln's act on it in the usual way. I'm not even going to write that down. The new thing is that there's also a condition for the gn's. Okay, gn on v is equal to 0. Let's call it the state corresponding to v is equal to 0 for all n greater than or equal to 0. This is the condition that it's a primary, that it's a superconformal primary. Right? This is the same as the condition of superconformal primarily we talked about when we discussed the superconformal algebra. It's just the same, the super analog of the similar condition. Okay. Now what we have here is, so what was our operator? Let's look at the Ramon sector. In the Ramon sector, our operator, our vertex operator was built purely out of psi 0 mu's. Okay, there were no creation operators of the bosons and no creation operators of the fermions other than psi 0 mu. Okay, of course this operator is this times e to the power ip dot x. Right, so we've got a vertex operator built out of this times e to the pi p dot x. So there's zero modes in the bosons. There's zero modes in the fermions and nothing else. Now precisely in the Raman sector, these G's are integrally moded. Any G1 or higher would have a destruction operator with 1 or higher of either the bosons or the fermions. So we'll automatically annihilate the state. The only condition from this that is non-trivial is G0. G0 has a term which is of the form psi 0 mu and alpha 0, let's call it alpha 0 mu. But alpha 0 mu, you remember, was momentum. So this is P dot psi 0. But what was psi 0 in spinor space? It was gamma. So it was P dot gamma on spinor is equal to 0. What is this equation known as? Dirac's equation. Okay. So the Dirac equation comes out of the BRST closed nature of the vertex operator. Okay? Now, oh my, I'm sorry, my diversion was a stupid one. I wasted a lot of time. Okay, I'll soon have to go, but let me finish this. Let us take a particular momentum configuration. We also, of course, the other physical state conditions ensure that p squared is equal to 0. Okay, so let's say that p0 is equal to p, p1 is equal to p, and every other component is 0. This is nice and on Marshall. So what we have now is p times gamma 0 minus gamma 1 on psi is equal to 0 on our spinor. Maybe I've been calling that S. On the spinor is equal to 0. Okay, if we analytically continue this to Euclidean space, to compare with the vertex operators we've been talking about, which were all Euclidean, we will pick up an I, and then this will be a traditional Euclidean gamma matrix, and there is an I. Okay, but what is this? This is simply a fermionic creation or destruction operator in gamma space. You know, where if you got two gammas, you have to go to gamma plus and gamma minus. So let's choose convention so that this is a an annihilation operator. So what is this Dirac equation in the language of spinors? It's telling you, the spinor has all these slots, right? The 0, 1 slot. I call it 1, 2, but you'll pardon me. There's the 0, 1 slot, the 2, 3 slot, and so on.
Yeah.
And what this is telling you is that this spin is frozen. Because it's frozen to, let's say, minus half. Is this clear? Okay, so let's say that there are some conventions involved into what exactly it's frozen into, but let's say it's frozen into minus half. So what's left, what you have left to play with? So basically this is the content of the Dirac equation.
Yeah.
P square equals 0 told you that thing was on shell.
Sure.
And then the Dirac equation tells you that in the 0, 1 plane,
Yeah, it just projects out.
there is a plane of momentum. In that, it just freezes the spin degree of freedom in that plane. That's basically what the Dirac equation is. What's left for free play
It's SO8.
is exactly the spinors under SO8, and this is how you make contact with little group analysis. But of course, something that was a chiral spinor here will also become a chiral or anti-chiral, depending on conventions. Spinor of SO8. Okay, with the conventions that we talked about today, this would become an anti-chiral spinor of S8. Because this has a 1 minus half, so there has to be at least an odd number of minus halves in the remaining. But there's a lot of convention that goes into this. What is not convention dependent is relative chirality. That's the only really important, only really physical thing. Right, whether you call this creation or annihilation is largely up to you. For bosons, creation and annihilation operators are totally different. Because A anticommutator A dagger is 1, but A dagger anticommutator A is -1. For fermions,
we can choose what we define as a vacuum state, right?
exactly, and the algebra is also the same. Sorry, I said anticommutator. A commutator A dagger is 1, therefore A dagger commutator A is -1. But when you have anticommutator, if A anticommutator A dagger is 1, A dagger anticommutator A is also 1, because anticommutator is symmetric. Right, so there's no difference in the algebra, there's no difference, Hilbert space is bounded on top from the bottom, there's no difference. It's
whether we call it state of field or a
exactly.
vacuum is.
Unless you have a notion of energy, but we don't even have a notion of energy here because these are all 0 modes. So it's really very convention dependent. If you follow a particular convention, you get everything right. But what is really completely not convention dependent is the relative chiralities. If you call one guy chiral, is this guy chiral or not? That there's no convention. Okay, fine. Okay, now the last thing I wanted to say is this. Okay, maybe I'll quickly try to say it and then we come back. Good. So we've got a feel for the vertex operators in the Ramon sector. When we had we've got a feel for the vertex operators in the Ramon sector when we had one guy in the Ramon sector and one guy in the NS sector. Okay, but now let's look at the Ramon sector. Now the massless operators are a spinor on the left and a spinor on the right. Okay? First question, what are the configurations that you get? Do any of you know what the rule for multiple? So now this is the question of Clebsch-Gordon, right?
Yeah.
You're multiplying two representations of SOD.
We will get space-time bosonic fields.
We will get bosonic fields, but which representations of SOD?
Yeah, also, there will be the mu fields, right?
You get forms.
Forms, yes. Yeah, right.
Okay?
Yeah.
How do you know this? Okay, you know this from many points of view. Okay.
Because of the Grassmann nature of.
Yeah. One way of thinking of it is this. Suppose you have psi alpha, you have psi beta. Okay? What representations can you by hand construct out of these? Well, you have to do this barring operation, which we should and will discuss in detail next class. Because you're familiar with it in 4 dimensions, but you may not be as familiar in arbitrary dimensions. I'll tell you what that means. But let me forget that for now, given that there's some such operation here, which effectively raises this index here. Okay? And then you could put as many gammas as you like in the middle. Okay. But how many gammas can you put?
Yeah, up to the maximum Clifford rank.
Yeah, say these psis are completely arbitrary, then you can put as many gammas as you have.
Yeah.
If you put 2 gammas of the 2 gamma 1s, well, gamma 1 squared then is 1, so you're not doing anything. Okay, so if you are doing nothing, if these psis are completely unconstrained, then the number of things you could put in here is 0, because you can have identity, or 1 or 2 or 3 up to d. Clearly, each of these is a d-dimensional. If you put m gammas, you get an m-dimensional antisymmetric tensor. Why is it antisymmetric? Because the gamma is anticommute. Okay, clear? Okay, perhaps this is So clearly these representations appear on the product of two spinors. Could it be that these are all that appear? Let's check. How many components do we have in a spinor in d dimensions without any further restrictions, no chirality or anything like
2 to the t over 2.
that? Right. Let's work with even dimensions just to keep formulas
Yeah,
simple. So that.
Because we are in 10.
Yeah. So 2 to the power d by 2.
Yes.
Okay. Now you've got one times another. So the total dimensionality of your space is this square, this times itself, which is equal to 2 to the power d.
Yes. And in fact, that's the Clifford generator of Clifford.
Correct. Now let's count. Now we have a guess that this Hilbert space is the sum of Hilbert space over forms. How? So what? Now, if we've got m index antisymmetric tensor, that is d c m coefficients,
Yes.
and the guess was we sum m is equal to 0 to d.
Yes. And this is 2 to the b.
This is 1 plus 1 to the power d, which is equal to 2 to the power d. I asked this as a question in the entrance exam before the TI for entrance exam. I mean, I didn't say Clifford algebra. I mean, the mathematics was the same.
We have the number from
Okay. Effectively, it was this question. Fine. Since the numbers match, it has to be right. Okay. So though you can give more formal group theoretic proofs, we don't need it. We've used physics to do group theory, which is always the best way. Okay. So, so we've understood that the product of two spinors gives you forms. Forms meaning antisymmetric tensors with indices running from 0 to d. Okay, wonderful. That was the case when we had when the spinors were unrestricted. But our spinors are not unrestricted. They're chiral. Okay? So suppose you have, now we have choices. Suppose you have S1 and S2. Suppose you have S1 and S2, okay, that obey the condition gamma 11 on S1, let's say, is equal to 1, gamma 11 on S2 is equal to, we have two cases, 1 or minus 1. And then we take the product of S2 times S1. Now what representations will we get? Okay. Well, this requires a little more work, but we can also figure it out using physics methods. Okay? And the little more work goes as follows. Okay, let me first give you the idea, but then we have to do it carefully because this requires understanding all this barring operation. Because barring involves with the gamma 0 exchanges chirality. Okay, so I'm going to give you the idea and then we'll do it carefully next time. The idea is this. Let's say that we've got S2 with this barring operation, whatever it is. And then some gamma mu1, gamma mu m, and S1. Now let's act on this with gamma 11. Since gamma 11 on S1 is 1, we've done nothing. Okay. Now we take this thing through all the gamma matrices and then through whatever in the barring.
I mean, it will flip a sign every time it goes through a gamma, the gamma 11
every time it flips through, goes through a gamma,
Yes.
it flips the sign as you said.
But the
Last thing, something
Yes.
may or may not happen. So
You can also fill the gammas which are there, right? You just replace them by which are not there.
that's if you start thinking of this gamma 11 as a product of all the gammas.
Yeah.
That's but right now don't do that.
I see.
Just take it through. Use the algebra. We will do that in a minute. Okay, and so you will get -1 to the power m, perhaps +1, and then depending on what sign it has on the S2, but some particular either +1 or -1, we'd be able to figure that out. Okay, now we do what Advait wants. But what does gamma 11 do? It just replaces it with the gammas that are not there. What is that known as in the language of forms? Hodge dual. Okay, so we get not forms, but forms with a particular Hodge duality condition. That under Hodge duality, these forms either go to either plus themselves or minus themselves.
self-dual or anti-self-dual forms.
Okay, and that will tell us what is happening. We'll come back tomorrow and complete this. Whatever, next time, complete this properly and go on. Okay, so we will go on studying these vertex objects. We'll understand the physics of these things. I wanted to show you, not today, I wanted to show you various things, including why when we wrote down supergravity actions, the natural Ramond fields didn't come with an e to the power -2 phi. Do you remember this? When we wrote down the string frame action, NS fields came with an e to the power -2 phi. Ramond fields didn't. None of you objected then, but you should have objected because our rules for e to the power -2 phi were in genus. All tree-level amplitudes had an e to the power -2 phi. Why were Ramond fields special? They're not special, but there's a story. I want to tell you about that kind of thing. Okay. Okay, we'll continue.